Couple quick announcements. So office hours open today in 2:15, so that's where I'll be over at 3 to 4 p.m. Same thing for next Monday, so no problems with those two. So you will have one more office hour day before the midterm, but it gets really busy. If you can, making it today or the TA tutorial extra time next week are good choices. I will have a review class this Friday. So this Friday I'm going to actually take and actually go over most of the material in a single sort of summary component. Again, no real building in questions. I'm just going to mainly go over the topics to give everybody a quick reminder. It's a good chance to sort of pause and go over the material one more time. Canvas Quiz 2 is online right now, closes at 5 p.m. on Friday. One other thing too, we had a lot of requests for an open quiz 1. So basically now that you've completed it, going back and reattempting quiz 1, that should be up now. There's a dummy quiz 1 which has all the different combinations, which means you can do it as many times as you want. Go for it, right? So please do check that. There will be a dummy quiz 2 that will also pop up after this one closes, so you'll have that to practice over the weekend. I also created problem set 1B is almost ready to go. Should release it today or tomorrow, so that gives you some more components. I have now posted the sample midterms. There are 5 sample midterms for you guys to go to, including questions and answers. I also created a decarboxylation problem set. This has been moved up. It's new. Basically, it's part of our content this year. Since it wasn't part of the kind of earlier progression stuff like that, I wanted to make sure you had some practice questions based on that. That is on the problem set tab of the Canvas thing. So a whole bunch of content for you guys to play with this week. And the midterms next week. So much fun. Any other questions? Yeah. Say it one more time. Yeah, content cutoff. Remember, end of slides for lecture 11, that is our content cutoff. So just after decarboxylation. Yep. Yes? Location for the midterm? Yeah, I think it's posted. Check the exam website, but I think it's over in the Chem building. I do believe I updated the points. I'm going to split up the, I have to look at their total writing, so it's going to be based on last name. I have to do a cut based on the seat assignment from that. All right. So last class, we started moving into carboxylic acid reactivity. This is reformatting carboxylic acids into other things. And the one we talked about is esterification. Remember, there's 2 classes of esterification. The alkylation class, that's where we're using our carboxylate nucleophile. And then we have our acidic esterification, where we're bringing in an OR group as our nucleophilic component. So which is the nucleophile, which is the electrophile in this pairing is the thing that changes. Under basic conditions, the carboxylic acid is my nucleophile with an alkyl iodide. Fischer esterification, the carboxylic acid formally is the electrophile, where an alcohol is your nucleophile in this case. And we just introduced the conversions to acid chlorides. So draw the starting materials necessary to make this thing via Fischer esterification. Okay. Turn to the person next to you. What is your answer? How did you come to that answer? Help to explain it out, especially if you guys see a difference. Go for it. Okay, and time. So the key here is we're making an ester, so target first. That's the functional group I'm targeting. Fischer esterification means I need a carboxylic acid and an alcohol nucleophile. I'll be under acidic conditions. And my product, the ester I'm making, is made up of the carbonyl component, comes from the carboxylic acid. The O and R, both of those species, is what's coming from the alcohol, which means that carbon-oxygen bond is the thing I'm breaking or forming. So the retrosynthesis of this should open that piece back up. So if I was going to draw out this product, my acid, and then making it linear, I can draw this out by saying, okay, that's carbon number 1, 2, 3, 4, 5, 6, 7, and 8. So I have now 1, 2, 3, carbon number 4 has my OH, and then 5, 6, 7, and 8. So we're breaking open this bond. This is a cyclic or an intramolecular esterification. And just generally when you're going back and forth in these parts, if it helps you out, this numbering scheme is a really good way to work through this, to look at the total bonding content, the atoms that are necessary, and actually sort of map out which go where, right? This is a 5-membered ring that's linking back between carbon 1 and the alcohol on carbon number 4. Again, one of the things that just as you practice this, recopying is a big problem, right? So slow down a little bit and just make sure that you're not doing alchemy, that all the atoms that you're trying to draw are actually present and you're not creating different points. All right, leaving groups. Which is the best, which is the worst? Yeah, turn to the person next to you. This one is going to be really critical as we talk through things today, so I want to make sure everybody's on the same page here. So work this out. What's 1, 2, 3, and 4? Okay. So, give me compound 1. Which molecule up here is my number 1 best leaving group? Chloride, not chlorine. Chloride, right? Yep, that's number 1. Everybody agree? All right, what's number 2? Carboxylate. That's number 2. Agree? Anyone want to challenge? Cool. All right, last 2. What's 3, what's 4? 3 is alkoxide. 4 is the amide. Amine, negative. Yep. Okay, how do you come to that conclusion? What rule are you applying here to help rank these pieces out? Remember, if you had to give a property to good leaving groups, again, you're talking to your family, it's over Christmas, over Thanksgiving, coming up for Valentine's Day, you want to make sure your mom understands what a good leaving group is. Yeah?
Something about the pK stimulants.
Yeah. Acids, first of all, these are all conjugate bases, right? They're negatively charged, they are bases. They're conjugate acids, so HCl, or carboxylic acid, or alcohol. Adding a proton to each of these creates my acid form. All those acids, I could rank them by their pKa. If the acid of the conjugate base you see here is a very, very acidic species, like HCl, that's a really good leaving group. That's one way to look at it. Saying that again, though, what are we saying about the properties of these conjugate bases? A very good leaving group is also what kind of a conjugate base? It's a super stable conjugate base, or the anion, this is a happy anion, right? What we're saying is that these, if you are a really good leaving group, you're pretty cool being negatively charged. So chloride is a really, really, really happy anion, and you reflect that, we measure that by looking at the pKa of its conjugate acid. The carboxylate, not too bad. So we could rank this, that this is kind of like, what, -5 or so, its acidic form. This is like 5, this is like 16, this is like 35. Whether those are reflecting the pKa's of their conjugate acids if I gave a proton back. So that's the same ranking and ordering. What we're focusing on, good leaving groups are happy anions. So that's going to come in. We start talking about manipulation or functional group manipulations around these kinds of states. What we're going to be doing now is looking at the carboxylic acid and doing what's called nucleophilic acyl substitution. It's related to SN1, SN2, so it means we're going to have a leaving group involved here, and the relative stability of the leaving groups is a key thing we have to think about this. It's a balance between the same kind of features that we talked about for substitution reactions, but now we're dealing with this higher oxidation state, the carboxylic acid, and its functional derivatives. So what we're going to talk about now primarily is taking a carboxylic acid and turning it to something else that looks like right? We're changing out that OH into other groups, and this could be OR, NR, chloride, acetate. There's a whole bunch of other permutations where that group over here can be many other fragments. For nomenclature, this general fragment, this alkyl group with a carbonyl, we call it an acyl group. So if we're talking about acylation, we're talking about transferring that functional group, our carbonyl, over to something else. So acylation of an alcohol means making an ester. Acylation of a nitrogen would be making an amide, things like that. But in the end, the conversions we're talking about, usually we're turning this into some other functional group which goes on a rank order of stability. There's certain reactions you can do or not based on what that Y group is. So these are the new players to talk about. We talked about last time acyl halides, where number one, the acid chlorides or acyl chlorides. Those are the main lifting group we're going to be doing. We're going to use that as one of our components. Anhydrides, they're called anhydrides because it's a condensation between what looks like a carboxylic acid and a carboxylic acid, where you took those two carboxylic acids and condensed them together. We remove water from those two, we make this anhydride type structure. Then we have our esters, where it's this OR group. Lactones are a special kind of ester, which is cyclic. We'll talk about those in the next slide. And then we have amides. Now, I've ranked these out in this order because this is something that we will come back to again and again. So right now, left to right, this represents reactivity. Acid halides, by far and away, are the most reactive in terms of their electrophilicity or rate of nucleophilic substitution. Then comes anhydrides, generally, then esters, and then amides. These are generally large different buckets left to right, and we have to use different reactions and conditions to react or permute between these guys. Now, as far as these two, these are just amides and esters, but they get a special name because they're cyclic. So lactones are just cyclic esters. Lactams are just cyclic amides. So this part here, that's my amide. This is my ester. The reason they pop up as a special name is this structure, just like other ring systems, 5- and 6-membered lactones or lactams typically are a little bit more stable and can be preferred than other systems. And also, this geometry comes up again and again in a lot of biological molecules. This is a very simple way to sort of loop things together. If anybody remembers amino acids like lysine, yeah? Lysine can form these cyclic lactam structures, which is the primary basis for a whole bunch of other biological signaling materials. Lactones like this are very useful as ways of sort of making these kind of packaged structures, which are very nonpolar and uses, again, as signaling hormones and things. The only other one I want to bring up are these two groups here. So imides is the name that we give, not imines, imides, I-D-E. Think of them as a special version of your anhydride. All you're doing here, and the reaction that you use to get them and how they work, they're in the same family as the anhydrides. They're just not quite as reactive in the same way that esters and amides are kind of cousins of each other. Anhydrides and imides are cousins of each other. The thing that makes imides really special, what we're going to come back to, comes down to this proton here. Now, this is a case where if I made this negative, if I deprotonated it, that negative is beautifully stabilized by resonance around this system. So we will come back to this in terms of functionality. I'm introducing it right now as part of your naming. Yes? What's that? Boop, boop. Yep. Yes, this is most reactive down to least reactive. And we'll go through the descriptions between them. So again, bringing up imides now for completeness. This is why we're introducing it now, because we just told you about anhydrides. Imides are just the nitrogen equivalent to the anhydride. We're switching this middle group here. And we'll talk about their reactivity later on. Nitriles, I'm bringing those up now because, again, you guys have seen these before. That is the same oxidation state as that carbon. We can hydrolyze nitriles to get to our carboxylic acids. That's why they're in this kind of galaxy of other functional groups as well. So, first part, all of these groups, the reactive players we talked about, so acid halides, esters, amides, anhydrides, they all have this commonality where they have two fundamental reactivity characteristics. All of them, just like we did with aldehydes and ketones, they are electrophilic here. There's a delta plus center at that carbonyl, right? All of them, because of that carbonyl, they have a carbon-oxygen pi bond, and most of the chemistry we're going to use is using the electrophilic character, this delta plus at that center carbon, and the fact that there's a carbon-oxygen pi bond that we are going to interact with. They're also somewhat nucleophilic at this center. This center here is our delta minus. That center, if I were to deprotonate, remove a proton from the alpha center, I make my enolates or enolate-like equivalents. So remember, these are not the same as our enolates. Because we've got a heteroatom in this position, they are usually harder to form. The enolates are probably easier, more acidic, but they have a lot of the same general characteristic. The analogy I'm drawing in here is everything we talked about for ketones and aldehydes really does come into play. So we still have this electrophilic center, this nucleophilic center. The major thing that makes them different is the nature of that Y group. What we put there totally changes which one of these groups will react in which way. So the amide, the ester, the acid chloride, or the anhydride, they all have this characteristic, but the degree to which we can use the electrophilicity or the nucleophilicity changes as we change what's in this Y position over here. So these are just, again, a callback. Remember, what I'm trying to emphasize is carbonyl compounds are carbonyl compounds. They follow a lot of the main reactivity patterns we talked about with aldehydes and ketones. Now, because we have this other complexity, we're going to have different ranking and ability to use them. This gives us more diversity of the kind of reactions that are possible. All right. So, pretty much all of these reactions follow a common pattern. This is what, in the couple times of the classes, I've referred to it as sort of the carbonyl Tai Chi kind of move. All these reactions follow a nucleophilic attack into the carbonyl group, and that's common what you've seen for things like imine formation or the acetal formation. The nucleophile is going to combine and attack that delta plus center. So most of what we're doing here as far as a kickoff is going to involve taking some type of nucleophilic species and adding it to that pi bonding type system. So this is going to change depending on what type of nucleophile we have present. That's the same sort of opening move that you've seen with aldehydes. The difference now, though, is if I were to take and add my nucleophile to this group and bump up, let's say, the electron density, depending if we're negative or neutral, we're going to form what we call a tetrahedral intermediate. So we go from a planar sp2 carbon up to a tetrahedral sp3 center. Now normally, if Y is equal to hydrogen, that's our aldehyde. If Y equals our carbon, that's our ketone. This is as far as we go, and the only move we have available is either get rid of the nucleophile again or protonate the oxygen. Usually that's as far as we take it. Now that the Y group are these other things, usually what we'll do is the second half of our Tai Chi move, we bring down that negative charge, and we have a choice. I could eject this nucleophile, which just takes me back here, or I can boot my Y group. And what that does is it takes me over to a new compound where the overall change here, that Y group has been ejected. We've taken whatever the center is, and we've done a substitution reaction. So this is where the analogy is SN1, SN2, right? This is the same thing as if I have Y. If Y is a leaving group, we're taking a nucleophile and substituting that Y group. The thing is, it doesn't happen in this one step like you've seen with a nucleophilic attack onto our sp3 center, Because we start with this sp2 center, we have to pull the charge up onto the oxygen and then bring it back down again to eject whatever that leaving group happens to be. So all these reactions follow this two-stage type process. We've got the nucleophilic addition. That forms a tetrahedral intermediate. That's our step one. That nucleophilic substitution then is brought back. We bring down the negative charge and we make a call. Do I want to boot the nucleophile or do I want to boot the leaving group? Booting the nucleophile takes me back to my starting material. Booting the leaving group takes me forward to my substituted product. Depending on what the Y group is and what the nucleophile is, this is where we get all the different permutations of which reactions are possible, which ones are going to be fast, which are allowable. It's that rank order that we started at the beginning of acid chlorides and hydrides, esters and amides. That ordering comes about because of the nature of what the leaving group is, how it impacts that first and second step, as well as what nucleophile we pair with it. So it's going to follow the same kind of general sequence of attack that you've seen with SN1 and SN2. Certain nucleophiles, good nucleophiles, will work with more of these substitutions. Poor nucleophiles are going to need certain matching with good leaving groups for reactions to work. So there's a kind of different, think of it like layers on an onion, of different kinds of reactions that are possible, really coming down to the nature of both the nucleophile and the leaving group in these systems. So the way we usually rank it out of what we consider allowable comes down to the relative rates that are possible. And it comes down to these three features, which you've seen these for back to SN1, SN2. What we call the nature of the electrophile, it's a combination of its electronics and its sterics. So very bulky things will make that nucleophilic attack difficult. If we have a very strongly electron withdrawing group, that's going to make the electrophile more electropositive, which is going to help out. The leaving group, that's the second step. Losing that leaving group is where we fragment that bond. That will make sure that we go forward in this process rather than dumping the nucleophile, let's say. And also what the nucleophile is. Bulky nucleophiles are not very good. We want very small, sterically non-encumbered nucleophiles. Also electronics, negatively charged things are better nucleophiles than neutral materials. But either way, the nucleophile is going to need some kind of lone pair in order for this bond formation to actually exist. Okay, so in general, this rank order, and this is why I'm layering it out like this, this is the common pattern of reactivity with acid chlorides being on the top of the heap and hydrides being next, then esters, and then amides. So if I thought, just for a second, think about this through. Why does, first of all, does this surprise anybody? If you look at these and go, I don't think I would order it this way, or any sort of general impression, is this something that if you look at this, something jumps out at you as like, that seems weird? Everybody's like, what's it? Midterms next week, so whatever you say, boss. Look at it just like this. If I look at, this is my common group, right? What I'm highlighting here is, that's the bond I'm going to fragment if I do a substitution, right? So I'm kind of trying to show you in that fragmentation, chloride as a leaving group, this acetate or this carboxylate as a leaving group, ester as a leaving group, or amide as a leaving group. What I'm highlighting through this sequence is, if you imagine doing this substitution, the group I'm kind of highlighting over is the thing that's going to have to depart as your leaving group as a negatively charged species. If you look at that, chloride as a leaving group, top of the heap. That goes back to our first slide, right? Chloride is a very stabilized anion. Acetate, or that carboxylate, I'm specifically highlighting this half of this group. Again, resonance stabilized, not too bad. Then we move to just O minus. If this was my leaving group over here, O minus is your leaving group that's going to be possible here. And then finally, your nitrogen. Those follow the same pKa arguments that we talked at the beginning in terms of the relative stability of the anions that you'd have through. So this ordering and ranking here is partly leaving group stability, but there's another feature that comes in and matters as well too. Look at these in terms of electronegativity. Which atom, chloride, acetate, oxygen, nitrogen, is most electronegative? Probably. Chloride's pretty good. Oxygen's up there too. But yeah, the combination here that you're seeing, the reason that you get this is you are using both these two features. The relative electronegativity, how hard we're pulling on that bond and making that carbonyl even more positive, and how good of a leaving group that is. What we're doing in this first step is we're not just saying which of these is going to be ejected. Remember, the leaving group potential really impacts this step over here, but whether or not a nucleophile even approaches it is also impacting this one. Depending on what we have here, if this is a very strongly electron withdrawing group, I'm actually changing how electropositive that center is, and actually in helping this first step as well. So they can act synergistically or against each other. Yes?
So if the leaving group is more electrophilic, is that always the case that it would be a better leaving group?
So say that one more time. Is which one?
If the leaving group is more electrophilic,
Yep.
will that always mean a better leaving group?
If the leaving group is more electrophilic, remember, electrophilicity is talking about how much delta plus charge is on this center. That's really impact of saying, take a look at this molecule, who's hauling on the sigma bond between this center and that center here. It's basically how positive is that center originally for that first step of our approach. That's the major thing here, is we're saying that in that first addition, to form a tetrahedral intermediate, this ranking of electrophilicity helps form that tetrahedral intermediate. Once you're there, the leaving group ability helps the second step, ejecting of that part or closing the tetrahedral intermediate to lose these. They do work mostly in the same direction, but there's a couple of features we'll go through in just a second. I'm trying to break out the two different parts of this overall attack. So generally, when we say electrophilicity, we're saying that, look, we're talking primarily about the electron withdrawing characteristics of this group. And the reason that this matters is, remember, just because this is electronegative, like the chlorine is a very electronegative atom, but remember on your rank, on your periodic table, what's the most electronegative atom you've got? Fluorine, right? Top corner. So chlorine is a little bit down. It's over in that area. Oxygen is kind of closer to fluorine, though. In terms of actual value, the single value of electronegativity, oxygen versus chlorine is kind of hard to sort of to differentiate, right? They're both very electronegative numerically, and I think actually oxygen sits a little bit more electronegative than chlorine. But chlorine actually ends up being a way more powerful electrophile because of the second feature here. If that group, if Y has lone pairs that can donate back into the center, you're going to kind of partially tamp out or depress the electrophilicity or this electronegative withdrawing characteristic. What I mean is a molecule like chlorine pretty much is just the electron withdrawing characteristics of chlorine. That's the only thing that really matters here. We're taking the chlorine center, we're hauling on the sigma bond, and that's creating this hole, this electropositive center here, that allows it to be electrophilic. If I took a molecule like an ester, OR, yes, it's very electronegative, even potentially more electronegative than chlorine, but because the oxygen, similar, remember these are both in the first row, carbon and oxygen are in this first row to each other, the lone pair in oxygen can donate back by my resonance structure. That's not the same case if we did with chlorine. Chlorine you can draw a resonance structure like this, but let's draw that resonance structure for just a second. If I draw this resonance isomer, chlorine here with a double bond and a plus charge, yeah, everybody should just look at that and oh my God, right? This is probably one of the most angry molecules or resonance isomers you can form. So legally, I can do this, but that is not okay. You're putting a positive charge on chlorine, and more importantly, you're using something from like a third row, using the lone pairs of that to donate back in. Those orbitals are completely different sizes to each other. That is not a resonance isomer that you're going to ever form in any appreciable level. Oxygen, on the other hand, same row. Oxygen and carbon in the same row. Yes, oxygen is more electronegative from a sigma perspective, but from a pi perspective, you're pulling back in. So this is why what you're getting is this push and pull. Induction is how you make things more electronegative or more a stronger electrophile along the sigma bonding skeleton, but the pi bond helps to tamp that back in. That's why if you get a pi donating system and a sigma withdrawing system, they can sort of rank each other out. So what we get is this. Let's go across each of them and add those two features. So, like we discussed, chlorine is a really, really good induction, +1, right? Resonance, nope. Do not go do that, right? You're not going to add electron negative back. So in the end, this becomes my number one electrophile. You're just using the electronegative characteristics of my halogen. We're drawing on this bond. We're leaving behind a very electropositive delta plus carbonyl. Over here, again, focusing on that center, oxygen is electronegative, so yep. Resonance, kind of, right? Because we have two things going on here. Yes, it's an oxygen. Yes, I can donate. I can also go this way, though. So the lone pair you have on the anhydride doesn't have to spend all of its time acting in resonance with one carbonyl. You've got another carbonyl as backup. So you've split it between the two. So that makes me ranking number 2. Esters, yes, you've got induction, but you've also got lots and lots of resonance. It's pretty happy with resonance. So the lone pair donating back to that oxygen gives you a lot of coverage where we're actually dumping electron density back into that carbonyl center. As a result of that, we get delta plus, and then here is like delta plus, and then here is like delta plus. Why is this one the bottom? So once again, amides are there, and this is also super happy. This is going to be number 4. Based on the sequence I've laid out here, why does that seem to make sense? Yeah. Yeah, you got two things going for you in that point. This is the most poquito one over here. One, oxygen is more electronegative than nitrogen in the same row. That's a head-to-head comparison. We can do that, right? So we can say induction is higher in oxygen, the esters, than amides. That's one. In terms of resonance donation, right? If I take a lone pair on oxygen and do resonance, I leave behind a positive charge on oxygen. If I take a lone pair on nitrogen and do resonance, I leave a positive charge on nitrogen. Which of those is better, positive nitrogen or positive oxygen? Positive nitrogen, right? So the relative resonance here, this resonance is better than that resonance because O plus versus N plus. This is not as good, so maybe make it a little smaller than this one for the same reason in terms of electronegativity. That's where this electrophilicity goes. And again, what I'm focusing on here is the first step of the two. In order to do a substitution from these molecules, the nucleophile must first engage with these ones. That's going to the tetrahedral intermediate. That's the stop on your way up to climbing up Grouse Mountain. So if this series right here is saying which of the tetrahedral intermediates, same nucleophile across all 4 of these, acid chlorides will easily make your tetrahedral intermediate, and hydrides, pretty good. Esters, okay, you're going to have to do some work. Amides are pretty much the bottom of the barrel. They're very difficult to attack. They are happy being amides, and they don't get nucleophilic attack easily. We got to do something with them. So this is generally that sort of general order and scaling. Remember, and we're focusing on the first of 2 steps here. Now, it does work out that the relative second step, the leaving group potential, really backs this up as well, too. But this is why we have that sort of fundamental change in the relative electrophilicity or nucleophilicity. So what you get here is a map. Now, again, this is one of those things. I have a couple slides that you may have noticed when Aaron and I are putting these together. We put these big purple bars on there, and this basically communicates that if you get this wrong, I will be very sad. What we're trying to say is this mapping gives you the roadmap of what you can convert into what. Acid chlorides with the right nucleophile can turn into anybody else in the sequence because of their relative reactivity. And hydrides easily come down to acids, esters, amides, but going from an anhydride up, walking uphill that way, that needs special characteristics. This jump from here back to there will not happen. Next, the esters and the amides, this oxygen series, they're more stable. Taking them down to amides, possible. Otherwise, to get from an acid back up top of the hill, we need this special short circuit. This is your gondola to get back to the top of the hill of your acid chlorides. And then finally, amides. Once you're down there, you're an amide. Enjoy. But this is how that sequencing works out, right? This here helps to put all 4 of these. Remember, these are not 4 fundamentally different reactions. It's the same reaction. Relative stability is what we're using to sort of convert between them. But it means that acid chlorides are phenomenal because I can easily reformat it to anybody on this list depending on which nucleophile I use. If I want to go from an acid chloride to an amide, I just use a nitrogen nucleophile to get in between the two. Acid chloride to an alcohol, or adding with an alcohol, gets me my esters. Or an acid chloride with a carboxylate as my nucleophile gets me my anhydrides. Yeah?
With the anhydrides, is there a way to control which forms which the oxygen?
Good. Okay, we will go in that deep. That's next one. The question right is, you've got a carbonyl and you've got a carbonyl. They are both electrophilic. You could attack one or the other. Now we need some special circumstance to hit the blue carbonyl and not the purple carbonyl. Yeah, we will talk about that later. Yes, you can, but that becomes the problem of using those. It's the consequence of this. You're right. Generally, we just use an acid chloride. Okay. So why are carboxylic acids not great electrophiles for nucleophilic substitutions? We talked about this last time. Nucleophiles are also what? Bases. So most of the time, if you take good nucleophiles, anionic systems like alkoxides, all they end up doing is an acid-base reaction to make your carboxylate and your nucleophile H. We've just transferred the negative charge from my nucleophile over to the carboxylate form. So this is why we have to do something with our carboxylic acids, acid chloride generations, whatever, in order to turn them into something else that's not a simple carboxylic acid. That's why these reformatting systems are going to be necessary. All right, so based on what we talked through here, let's rank these. Which do you think is going to be the best or worst in terms of nucleophilic substitution? Yeah.
Is there a way, if you use a nucleophile and you use a stronger base than that nucleophile, would it?
For the carboxylic acid? No, because if you use a stronger base, if it's there at all, proton exchange still happens. The base is still grabbing that hydrogen, right? So you'll still take the carboxylic acid into the carboxylate, and now it's not electrophilic at all, because you're dumping in all this negative charge to that center. It's a brick. You got to do something, yeah. What's in Helen?
Why is it Cl and not F? Like
Oh, F would work. We don't usually use F. We'll talk about that in a second. Byproduct of an F reaction?
wait, is it the byproduct is like
Hydrofluoric acid is problem one. But what you get is, it's interesting in the halogen series. Let's talk about it after class. We're not going to do that one today, but that's a really good question. Okay. You have 4 molecules to rank. None of them are the easy gimme of like, oh, it's an acid chloride. These are all oxygen. You know, the leaving group in each case is an oxygen atom, right? So how do we divide this up? Give me a strategy for how to attack this problem here. Yeah? Yeah, if you go through this, yes, the oxygen is kind of common, but this one and this one are anhydrides. The other ones are what? If I had to name these, on the farthest left, I call that a ester, but more special ester that's in a circle is called a lactone. Yeah, then we got an anhydride, then we've got a normal ester, and then we got another anhydride. So break them into 2 and 2. Both anhydrides are going to beat both esters, right? Yeah. That's good, yes. So here, we're going to say these are going to be 1 or 2, 1 or 2. I would argue that's going to be 1, and that's going to be 2, because sterics. The carbonyl I have to attack here is less sterically encumbered than this one. Fun fact, that's called a PIV. Pivoyl. Ha ha. Anyway, don't worry about it. This is what we do when organic chemists get together, and they're just like, how many named reactions do I know? Ha ha ha. It's like really bad quiz night. But that gives you these 2. Now, we're down to these ones. So this is 3,4, and this is 3,4. Which is 3, which is 4, left or right? So 3 is going to be right, 4 is left. Why? Sterics again, yeah. This is probably 3. This is probably 4, because again, that approach is somewhat encumbered over here. Now again, this might be a little bit tight. I have an unencumbered, number 3 we've labeled here, not sterically encumbered. Number 4, yeah, we got those methyls next by, but I have a 5-membered ring, which is kind of spring-loaded, maybe. Not going to talk about that, right? But you know, that's something that might confluence with. But this is mainly to go through and say, in terms of sterics, nucleophilic attack, the first ability to add, when we're talking about the electrophilic character, we're talking about the ability for something to add to this carbonyl, so that ring opening part doesn't matter. That's the second step of this process. Yeah? No, once again, remember, what I'm focusing on here is I'm saying rank which electrophiles for the substitution. What I'm saying is focus on this first step. Which nucleophile will attack that carbonyl better or worse? I'm only saying I want which of these is most electrophilic. Ring strain, cramming in the ring strain, is mainly going to help with the ejection, opening, breaking the carbon bond, which is the second step of your acyl substitution, right? Okay, so now let's go to the second step. Oh yeah, sorry, please. Yep. Yep. Oh, is this? Oh no, left. This one. Yes. Is that more reactive than amide? Yes, by a long stretch. So these categories, we have the buckets of acid chloride, anhydride, ester, amide. You rank things according to those buckets first, and then we move within the bucket. Absolutely. Yep. So that's the first step. That's the nucleophilic addition, the relative ability to influence these as electrophiles. Now we're going to talk about the leaving group, which is affecting the second step in this process. If something is a happy anion, we get them and we show these as good leaving groups. So if you look across the series, the same trend also persists. This is a phenomenal leaving group because chloride is a very stabilized anion. The carboxylate you form here, pretty good. Alkoxide, not end of the world. That is horrible. Doing this, like the nitrogen minus that you would form as a leaving group, is right at the bottom of the barrel. Almost impossible to do. In fact, the only way we can really do amide bond breaking is with an acid catalyst. We need something there to help that nitrogen become a better leaving group in the same way SN1 requires acids to take alcohols into better leaving groups. So generally, if you're talking about this, for the nucleophiles now, the nucleophilic partner, same rules apply from substitution reactions. Anions are generally better nucleophiles than neutral species. So we're looking for things like O minus, R minus, carbon minus, like this. Those are good nucleophiles because they're anionic species, which are going to act as generally very strong nucleophilic components. Those strong nucleophiles are going to be necessary for anything on the bottom sort of list. Esters need things like these strong nucleophiles to work. Weak nucleophiles are things with lone pairs but are neutral themselves. So these are like alcohols, water. Those will react with things like acid chlorides and anhydrides. Weak nucleophiles probably can't touch esters, amides at all. We're going to need something else. And just like before, we can help to rank these where sterics helps us with this case too. We can actually differentiate between an O minus and a different O minus based on how sterically encumbered there is. But we actually work through the sequence in terms of these kind of bulk categories first. The relatively good nucleophiles will all be negatively charged, and that's our primary feature that drops it in as a strong nucleophile. And then we use these smaller features like stabilization on that O minus or the sterics on that O minus in order to rank which nucleophile might beat out. But this is the same kind of thing that we try to teach you guys through. Try to start with these primary categories as your big buckets, and then you do small perturbations within those to change out. So overall, once we've got all these different pieces, we can use these 4 categories in different ordering in order to select which functional group is going to work against a different one. This is also going to allow us to select between different kinds of esters or different kinds of amides, depending on our nucleophiles that we use. But it's these 4 different categories you're going to work through. In general, and we'll try to emphasize this part as we go through, if a reaction is very easy, it can happen at low temperature. Acid chlorides, can use almost any nucleophile you want. When you go to things like anhydrides, Now you're going to have to work a little bit. You may need higher temperatures, better nucleophiles. When you go to things like esters, temperature is definitely the game. You're going to need O-. You're going to have to really, really try to get over this barrier and beat the relative stability. When you actually go to things like amides, you need acid catalysts. There's nothing that's going to happen unless you actually get to something else to really help it out. So this is where we get this sort of order and ranking that you've seen through. All right, that is it for today. I'll see you guys on Wednesday.